you for having us. It's a pleasure to present for AI3SD Online Seminar Series. Today we are going to introduce you to our current ongoing project and the title is Artificial Intelligence New Clause from General Purpose Technology to Large Technical System. A small insight in the title, if you want to be interested in that the Artificial Intelligence New Clause refers to a book of Roger Penrose, who wrote a book on artificial intelligence, general intelligence, and there is a whole discourse into this field. And the new clause relates to the fact that we try to suggest the alternative framework instead of considering artificial intelligence as general purpose technology, which we will discuss today, and replace it, or at least complement it, with the other consideration of AI as large technical system. So with any other ado, we will proceed. So first of all, the AI is already expected to be a pervasively applicable technology. So there is, of course, a premise to make this statement. However, every single next big thing very often and very quick acquires the label of general purpose technology. So by the virtue of being large or by the virtue of being important, technologies can be put together in this big category of next big thing. But these big things are not homogeneous within. And the general purpose technology concept is a specific concept that delineates a specific family of technologies, not just every single big or successful. So, and we claim that equalizing AI and GPT concepts, I will be referring to general purpose technologies shorter as GPT. So, equalizing these two concepts is not only incorrect, but it's also maybe detrimental, because if the aim of consideration and in general governing AI as a big thing, indeed, it is to understand and predict, then wrong consideration might lead to wrong insights and wrong conclusions about this technology, how it can evolve, who is important actor, and what exactly we want this technology to perform and how to, which results to achieve. So we fit, for this reason, we fit AI in an alternative theoretical framework of large technical systems, which we perceive as a better suit concept in order to discuss the implications of AI as the big system technology. So, first things first, we will go through these three big concepts of AI, artificial intelligence, general purpose technology, and large technical system. We will start with AI because it is a big object of our research, and we will go through a very aggregated idea of philosophy of AI, briefly though, to more fine-grained levels, and we will just name some applications of AI as a technology. So AI in philosophical terms has two approaches, so two considerations. One is weak AI, which is specialized algorithms, and stronger or general artificial intelligence. So this general artificial intelligence, I already cited it. There is a book of Roger Penrose who wrote exactly about strong artificial intelligence. And this distinction is important because weak artificial intelligence, it only emulates the intelligent behavior, high intelligent artificial behavior, instead of recreating it in silico, which would be stronger artificial intelligence, general artificial intelligence. And seemingly very aggregated, very far from practical life distinction actually has practical implications, because strong artificial intelligence would be able to deal with all possible contingencies of the world that an algorithm, a virtual machine, needs. While weak artificial intelligence is a very specialized virtual machine that has a specific data on which it runs, that has a specific purpose in maximizing function under its engine in order to fulfill and obtain the goal. And what we consider in our research is an all artificial intelligence that is current artificial intelligence is weak. In the weak domain. So it is a specialized virtual machines. There are two approaches. There are more than two, but discussed, and one of two of the most successful ones are connectionism, which are statistical learning data-driven algorithms, neural networks, we all recently heard about them, and symbolic rule-based programming. So symbolic approach it has the different way how to emulate intelligent behavior, setting up the set of rules according to which the information processing happens in order to achieve the goal. What we consider in our research, it is this weak connectionist AI. So we consider specialized algorithms, which are mainly neural networks that are trained with reinforcement learning or with supervised or with unsupervised learning, so deep learning also included, but weak connectionist AI. Regardless the approach, any artificial intelligence would need a constituents, elements that comprise the whole, the technology itself. And the technological domains that constitute artificial intelligence, they are undoubtedly algorithms, so the software, virtual machines that perform the analysis or perform the information processing. Second, computing power, so the hardware on which it is run, and then it also gets more specialized in recent years or more tailor-made to process exactly AI virtual machines. Third, it is input data. So in order to make the algorithm run, it's like blood in veins. It should be some data that one can input and then process this information. So information should be coded in order to be an input for the algorithm. Fourth and last, domain structure. It is a bit elaborated concept, but it is a sort of environment in which the algorithm performs. If one recalls any computer game, the environment would be the environment in which the character or object that we operates inside. So for robots, for example, if artificial intelligence is embodied in robots, then the environment would be the physical environment, either simulated or the real one, in which they would have to navigate. These algorithms, they of course perform very diverse. That was one of the breakthroughs, that now the set of functions that artificial intelligence algorithms can perform expanded. And the raw data was harnessed, and now algorithms are more successful in audio and visual recognition, natural language processing, and predictive analysis. There are many other functions, but just to name a few. And these functions, they are useful and they can be commercialized by applying them in some economic activities. And for example, it could be telecommunications, transport, fintech, medicine, so discovery of drugs, of protein structures with algorithms of artificial intelligence already takes place. Analysis of radiography, X-ray already taking place, and already some results are achieved, sometimes even above human performance. So our object of analysis, what we look at a specific instantiation of AI in all its complexity, it is this weak connectionist AI, as already said. And it has these four constituting technological domains. So, but what is then GPT? What's that the concept? This is a concept from evolutionary economics. And GPT as a technology comprises a class of radical technologies that are characterized by three features. First of all, general purpose technology should be generally applicable. So it is widely used and it has many uses. We will elaborate on that slightly later in the presentation. So technological dynamism in itself, the technology evolves. So it's not stagnating, it achieves new and pushes the frontier further in what it can do and where it is applied. Innovational complementarities, GPT should create in downstream sectors, in the sectors in industries, firms. It should create these innovational complementarities in the sense that it fosters innovational activities and processes inside these downstream application sectors. So why it is important, why this concept in general was invented in economics, it is because these general purpose technologies, they try to capture the dynamics of growth in economy. So that once introduced and deployed, these general purpose technologies, they create these fluctuations, these long waves of development characterized by different stages and rates of growth in the economy. And they are the focal points of coordination between GPT using and GPT producing sectors. So there is this coordination between the GPT as a component and the application sectors where it is used. And this coordination can fail. And hence there is a need for policy or public intervention in order to restore the coordination and boost the growth again. Here you can see on this graph a small illustration. It's from a seminal paper of Bresnan and Reitenberg, one of the founding fathers of the GPT theory, along other authors. But this one is one of the seminal. So this semiconductor represents a GPT, and GPT has this pairwise bilateral connections between GPT, which is upstream, and downstream many application sectors, so which you can see as hearing aids, computers, CT scanners, and all other technologies that embody inside semiconductors. So GPT has the structure of one component to many different application sectors. So it's a sort of ego network. So now, knowing though briefly, if you did not understand something, if it's still something unclear, please ask your questions in Q&A, and we will happily answer. So if we match AI against the GPT characteristics and the essence of what we represented as a GPT, according to the theory, we will see the following picture. So first of all, as I already said, general applicability or pervasiveness. So many uses, one of the components of the pervasiveness feature. It means that the technology has many functions, so it can perform diverse set of functions that can be commercialized in different applications, which is indeed true for AI. Many different industries, life sciences, medicine, autonomous driving cars, and so on, many other, whichever you can come up with, online commerce and marketing. Many uses indeed taking place, many functions. However, not widely, AI as a GPT would be not widely used. So it does not really fit here, because widely used means that this business heavily relies on the AI as a technology. So it is a core component, and without this component, the whole system, the whole business model would not work. And in this sense, AI actually does not fit to many industries, because though applied in many industries, only one actually relies heavily on it, which is online commerce and marketing. So inside each company, it takes rather functional replacement, like HR or marketing analytics, or I don't know, project application screening. So it is a functional replacement. And very often these functions are not even core functions for the firm, or neither for the industry. So this function being replaced, if it is, for example, exploration of mining of ores, then exploration can be taken, can be done with itself algorithm analyzing the data on the components of the soil. So the direction where to bore can be more or less navigated by AI, but the extraction and the processing of ores would still be done in completely non-reliant on AI algorithms manner. So the complementarity that it does create, but it is not reliant on at scale, and it is not a core component. And even more, there are substitutes. So there are close substitutes that well, previous technologies, though maybe less efficient, but still the same functions can be done with other combination of technologies. And that makes AI not really fit to the idea that it is a GPT. In the overall, only a small fraction of economy indeed relies on AI at scale, though many users are present eventually in many other, in the economy. Not many of them are at scale. So it is rather a capital deepening in companies where it is indeed deployed at scale. And it is a localized transformation rather than overall consuming transformation of the whole economy. So to prove the statement, instead of theoretical framework, to prove the statement with the data. This is a AI index report done by Stanford University for American companies in 2019. And here on the left side, one can see the industries. So the industries where the AI jobs are posted. So you can see in this graph the share of AI jobs posted in percentage out of total by sectors in the USA. So we see that many industries post some jobs that are related to AI. But if we give a look at the, maybe you do not see it perfectly, but I can tell you for sure that here there is 2.5% only. So the many industries indeed post, but at a very, very, very small magnitude that they really need AI labor. Sorry, this is the other, it is annual business survey of 2020 by US Census Bureau. And here there was a survey asking firms at which, to which extent did your business rely or use a specific technology in order to produce its products or services. There are many other technologies, not only AI technologies, but for example, AI-related technologies like machine learning, natural language, automated vehicles, voice recognition, robotics also to some extent. So some technologies represented in this survey are related to AI and belong to the cluster. And we can see that among 500,000 firms, only 8 to 9% report at least one technology. So in general, the numbers are very small. So technology might be reported as used even less than 5% or between 5 and 25%. So very few firms indeed use AI at scale. They rather test, use it a bit, and only those who said yes in general, they are only 8–9% out of 500,000. So it is a very, very small amount of pool firms, and also inside them, they are testing it rather. So technological dynamism. Technological dynamism talks about how the technology itself evolves over time, and just to somehow track the evolution of, for example, so the domain of algorithms. One can give a look to these two quotes. One, it is from Dartmouth conference draft. It's a paper that they published after this actually perceived very important and it is indeed important conference, summer school, that all the founding fathers of artificial intelligence participated and came to some goals, conclusions, and strategies in order to achieve, in order to progress in AI. And in 1995, they already back then acknowledged that maybe speed of computers and memory size are not sufficient to achieve the goals of simulation of higher functions of the brain. But actually, what is more important even than memory and speed of computation is that ability of an algorithm that can bring to this goal. And then the same conclusion was repeated recently by Stuart Russell, a current specialist, a current expert in AI, who also reported that running poorly designed algorithms on a faster computer does not make the algorithm better. So it just means that you get the wrong answer more quickly. So faster does not mean achieving the goal. It just means faster toward the wrong purpose and faster toward the right purpose. But what would it mean to achieve the goal? It is to write better algorithms, right? The algorithms that really can simulate the higher functions of human brain. And given that these two statements are separated by roughly 70 years, means that inside technological dynamism takes place, and breakthroughs like reinforcement learning and deep learning indeed proved some progress in AI, but it is rather leap-like. It is not a continuous, or at least maybe it started after the breakthroughs. But for now, technological dynamism of AI might be overestimated. And what is more important to note from these two quotes is that both data and hardware, they are of equal importance with artificial intelligence. They constitute a holistic system that represent AI as a technology and cannot be considered in this section. To prove also that statement, or to give some evidence, there is example of ImageNet competition, visual recognition in 2012, which the breakthrough was possible because this data set of images labeled in general was created in order to allow for a benchmark and for the training to take place. The GPUs, the graphic processing units, started being used to train the algorithms to be able to, in general, compute in a decent time in order to find the architectural structure of a neural network. And deep learning that allowed in general to make, this is exactly the component, algorithmic component, which these two quotes are talking about, that it is something that allows you not only to arrive faster, but also to indeed come to the result. And deep learning exactly did that. But in general, the achievement could have appeared only due to coming three sibling domains of data, hardware, and algorithm software. So lastly, innovational complementarities, they have to do with rate of innovation. So AI should create faster rates of innovation inside its application domains. And indeed, AI does influence the rate of innovation in user sectors. We already mentioned that AI indeed fosters innovation inside different fields. But it is still a sort of a component to the input to the innovation process in sectors users of AI. And also what is more important is this inducement can occur, so the inducement of innovation processes in downstream sectors, in the sector's applications, can be done through all sibling domains and not in isolation only one of them. So that algorithm cannot function well without proper data, nor algorithm can be applied if proper data markets and proper data simply does not exist. For example, medical data, if data is not available, one cannot train the algorithm, one cannot say whether it performs good. But then it needs to organize better data markets or somehow to organize in general the transfer of data, keeping in mind the privacy debate in order to make this algorithm function, to keep them explainable, and at the same time to bring the innovation, to boost the innovation in this medical sector. Lastly, the logic, the AI changes the logic of how the innovation activities in downstream sectors are performed. So it is AI is an invention of method of invention, it was labeled. So it is a data-driven discovery, and due to the success in statistical learning techniques. And also progress in computation power and progress in creation of databases where they can test the algorithms, the developers. And this AI, it brute forces the knowledge space, so just passing through very fast through all the possible large share of possible contingencies in order to find, for example, the structure of the protein that is promising in order to deliver the properties that this protein needs to deliver. So in this sense, AI is qualitatively different from what GPT is, which is a simple technological component that builds in bigger system that does not include, so GPT is a component, and the system in which embeds this component is a separate thing. So, so AI is once again qualitatively and procedurally different from GPT in a manner how it delivers innovational complementarities and in a manner how it affects innovational processes within user sectors. Now we proceed to the definition of large technical system and fitting this concept on AI, and my co-author and colleague, Dr. Simone Vannuccini, will continue from here.
So thank you very much, Kate, for the great first part. So if one reads the economics literature on AI, indeed everybody label AI as a general purpose technology. But as Kate has shown you, it is clearly a definition that tends to miss the mark. So our aim was to find an alternative framework, and we identified a framework that has been developed not in economics, not in technology field, but in the so-called science and technology studies field, or in mostly in the sociology of technology field, may be a good candidate. So a large technical system is a specific conceptual construct that has been debated at length. It does not even have a so precise definition, but in general, it is a socially constructed and socially shaping complex system that puts together, that combines together technologies, so technological components, actors and resources that are involved in the production of these technologies, regulatory bodies and institutions that contribute to setting the stage for the production of these technologies, and this system somehow coordinates to serve a sort of a common goal. So large technical systems, there are examples of large technical systems in, if you want, infrastructural technologies that were the large technical system at the time in which the concept was developed, so in the 80s and the decades around. In general, they indicate so infrastructure. There could have been telecommunication system, could have been local transport system, energy deployment system, but also recently the internet. So large technical systems are characterized by an evolution that passes through some phases and the acquisition over their evolution of a specific style, so a certain configuration. And most important, their change over time, their deployment and the formation is driven by certain driving forces. These driving forces are interesting to us because compared to what other technologists would do, looking only at some of the technological component of AI, or an economist would do, as Ekaterina said, looking at the incentive structure, for example, for innovation in downstream industries, these are socio-technical driving forces. So elements and building blocks that shape the functioning of the system. So what we do is we try AI on these different clothes. Before going into that, a bit of definition of what the elements of the large technical system, or LTS, as we are going to mention from now on, is. So each LTS, along its evolution path, passes through distinctive phases that go from the invention, so a new technology system emerges around the radical innovation, then it passes through the phases of development, so test of the system in specific test sites, for example, then it reaches the phase of innovation in which it somehow adds elements, features to the main technological core. Then it grows and enters the phase of competition in which let's say the system is commercialized or is released in the wild, if you want. When it starts to work, it passes through the phase of consolidation, which has to do with acquiring so much autonomy of functioning that it's become an object in itself. And finally, an interesting thing also that the literature on LTS highlights is the phase of technology transfer, in which one large technical system developed in certain context is taken and applied elsewhere. Now, this is indeed what is happening with AI, where you see that AI system deployed in, I don't know, countries or supranational contexts like the European Union or the US are then taken and adopted elsewhere. So it's a system subject to a technology transfer in a large sense. What are the driving forces in general of large technical systems? These are interesting concepts. For example, one is the concept of reverse salient, which shares some similarity with the concept of bottleneck, but is a bit more elaborated concept, because the reverse salient are the component of a system that have fallen behind. So they've fallen out of phase with other components. Why is this important? Because the reverse salients are sources of critical problems. And when critical problems appear, then innovative effort and resources aimed at innovative effort can be allocated toward the solution of this problem. So identifying the reverse salience of a system allows to understand in which direction innovation can take place. Indeed, as Rosenberg, one of the main scholars of economics of technological change, would say, reverse salient are focusing devices. So they are mechanisms through which actors active in the production of a technology can identify where to innovate, where to introduce change. A second concept is the one of system builder. So system builder also is similar somehow to the concept, for example, of entrepreneur, but it has a wider, richer, thicker meaning, because the system builders are the actors that perform the socio-technical weaving necessary for the formation of an LTS, meaning are these actors that, let's say, tie the system together, form and maintain the linkages, shape the linkages, if you want, also based on their own propensity or interest. So they can be inventors, they can be entrepreneurs, they can be managers with engineering capabilities, but they can also be large firms. So these are the actors that contribute to the shaping of the technological system. Other two important concepts are the load factor, which is purely engineering or physical concept, because the load factor has been studied by scholars of LTS, and it is the ratio of the average output to the maximum output given a certain period of time. And this is an indicator, a metric, a quantitative indicator to measure how a system is in use, if it is at full capacity, if it develops some tensions, or how the work, the useful work for physical system, but it would be the informational work, if you want, for AI is distributed among its parts. And this is also important because understanding where the system is loaded, so which is the load factor of the system, can direct the expansion of the system, the effort of actors, the adjustments driven by policy, for example. So this is also very useful. And finally, another concept is the one of momentum. And the concept of momentum or dynamic inertia is the idea that a large technical system gains strength on its own. So it gains a degree of autonomy as long as it becomes consolidated. So it's very hard to remove the system. You should imagine it once again as a physical system that gets indeed physically momentum. So it's hard to stop as it advances. And a large technical system that acquires momentum become less sensitive to pressure. So it becomes rigid, harder to modify, change, remove, or adjust. So the idea is that this concept, the very idea of a large technical system and the building blocks and the driving forces behind the evolution of a large technical system, they nicely fit to AI. Indeed, if you take AI as we consider it, so the weekend connectionist AI, first of all, one thing that we can do, we did in our paper, is to recognize the feature of LTS in AI. So first of all, AI, so to say that the AI is a large technical system, assume that the AI is technical because it includes technological elements, AI is large. Why it is large? Usually the literature on LTS, even though large is a bit of a fuzzy concept, suggests that a technology or a technological system can be large in terms of territorial coverage or user coverage, or it can be large in terms of the size of the actors involved in the shaping of the technology, or it can be large in a sense that it produces far-reaching socio-economical and environmental impact. Now, if you take AI, AI is large in terms of potential user coverage, is large in terms of the actors involved, it is large in terms of the far-reaching consequences that it can entail. Be aware that it's once again different from the distinction that Ekaterina made about the AI having many uses but not being widely used. So AI can be large with respect to these categories and still representing a small set of functional activities inside firms or offered services. So AI is large. Second, AI is a technical or technological system. Indeed, as we already discussed, AI is a system of components or is the network of technological domain that includes at least the algorithm as the software, the hardware, so the computing power, and the data. So already in its very basic definition, AI is a system. So AI is large, AI is a technical system, AI is, we at least can recognize the feature of LTS in artificial intelligence. Now, if you look at the building blocks of AI, we can recognize that these exist in the current evolution of AI. For example, if you think about system builders, the AI large technical system has currently, so which is the status quo, has currently a set of different system builders that weave and form the technology. One, for example, is AI using companies, and these are the companies that are the recipient of the technology, that they experiment with that. If you give a look to the recent book of Competing in the Age of AI from Yanciti and Lacani, they would suggest that these are the companies that try to implement AI in their runtime, so in their logic of functioning. Once again, limited logic of functioning, functional space of the total activity they perform, but these are the actors that by adopting AI and reinterpreting it, they shape the system. Even more shaping the system are another type of system builders, which are the AI producing companies. So these are the inventors, developer, and those that owns the essential asset with respect to the AI functioning. So they are the gatekeeper of the AI system, and the GAFAMs of Google, Amazon, Facebook, Alphabet, and Apple, and Microsoft are the big tech giant here. And if you look at some example for, this is exactly the case, that these actors shape the system, they build the system. Think about Google, that at the same time develop the programming framework of TensorFlow, so it creates an environment or a standard to the progression of AI, one of the component of AI, which is algorithm. It has in-house developed hardware, so TPU, tensor processing units, system for the calculation, and it also has Google Cloud for the storage and repository of data. So this is a system builder that acts on the different elements of the system in order to shape. At the same time, the system builder, they can steer the system in the direction that they want. You know very well that there is a long discussion on the validity and importance of the foundation of ethical boards and doing voluntary pledges and developing guidelines in order to regulate or not regulate the evolution of AI. So the AI has system builder that steer and weave, steer its direction and weave its function. AI has changing boundaries as a system have. So we have witnessed the emergence of big data. We have witnessed the improvement of performance of AI system over a large set of tasks. For example, this data EFF is the Electronic Foundation Frontier that kept track of that until 2017. We saw the expansion of the compute as the hardware system, as OpenAI nicely put it, compute has been doubling every 3-4 months, so at exponential rates. You have that AI has been emerging from rather obscure computer science department interest to industry, and now to grassroots mobilization that have to do with, for example, face recognition technology and so on and so forth, and an increasing interest in decolonizing AI and having a more inclusive approach to AI. And AI as a large technical system have different styles. So you see everywhere developing national and supranational AI strategies, and therefore the increasing debate if there is an AI arms race, so a competition between systems, especially between the Chinese approach to AI and the American approach to AI, or the European approach to AI, somehow trying a moderating position in between. What also AI has, if AI is a large technical system, is that AI can take different, so an issue important for a large technical system is how control is executed or formulated, and you have that AI can have different ways in which control over the technology is executed, so it can be more centralized and more decentralized, with advantages and disadvantages for these different regimes of control. And finally, we said in the definition that a large technical system should have a goal orientation. And this goal orientation can be more or less overarching, more or less aware in the actions and behavior of the system component, system builder, but nevertheless being there. So Ryan Kahlo, a legal scholar, put it very simply like the role or the meaning of AI is to spot patterns that people cannot do or spot, and these apply everywhere, or its goal could be the elaboration of a vast amount of data. We suggest that if you want a missing idea of interpreting AI as a general purpose technology, for example, was to not to give a clear idea of which is the goal orientation of establishing AI as a overarching infrastructure, and we suggest that this could, in the end, the goal exists, and what it is a cybernetic goal, because it is a decentralized or centralized, coordinated or uncoordinated attempt to shift the fabric of control of the society, so the way in which control is executed from the human-based domain to an automated domain. So every act or every instance of control can be based on instances of adaptive prediction rather than human or top-down decision-making. So if we start to look at AI as LTS, we see all these features that AI has. And then as a last, let's say, contribution that we can give is to map AI or the features of AI on the dynamic drivers of the evolution of a large technical system. For example, we discussed that the large technical system has reverse salience. Which are the reverse salience of AI? And we identified different reverse salience. For example, in the hardware domain, the fact that computing power of chips is falling behind the advancement in and the requirement and the needs of computation of AI. We highlight that in another paper on the trajectories of recent trajectories of the semiconductor and chip making industry. Or another reverse salience or source of potential problem is the fight and competition between two alternative models of organization of the computing infrastructure. So there is an increasing debate if to design architecture for computing toward the cloud with the related issue of control and distribution of power, or toward the edge, so in a more distributed, let's say, device-embedded manner. So these are sources of potential problems. And when you know the sources of potential problem or critical problems, you might decide where to intervene as a policymaker, for example. So you can have a more peer-to-peer kind of architectures or more top-down big tech controlled architectures. The data domain is also a source of, is also a contains reverse salience because the way in which data is stored, managed, accessed, and maintained, we have emerging critical problem if, for example, to store data in public databases or if to organize data markets, but how data markets can be organized, how pricing can be established. You know, there is a huge debate on the data as value, data as labor, data as intellectual property. So the collective and coordination, how the system should behave, as suggested by AI being a large technical system, will influence the solution of the critical problem and the evolution of the technology. The same holds for the algorithmic domain. So our algorithm evolving, will there be a turbulence in different systems? Will there be the emergence of some sort of what are called in economics dominant design and dominant environment for algorithms? So these are important elements that the LTS approach suggests. Another set of elements have to do with the load factor, related elements. So for example, as we said, the load factor is how the tensions in the operation of the system are distributed. And as the system grows up, there are what the economists would call learning by scaling. So by growing up, the actors learn where to improve or where to relocate resources. Or as the economists would say, there are economies of systems. So the technology and the participating parts of the system learn how to better organize it. And this does not have to be frictionless. So this can be conflictual. And the example here is the existence of alternative ways of computing or running or feeding algorithms with data between, let's say, large troves of data stored in the cloud and run through the algorithm in a controlled way by the digital giants, or the alternative of instituting a system of federated learning. So federated learning in which computation occurs directly in the devices, and then, for example, only the values of the gradients are sent up to centrally stored deep neural network or algorithm, and so on and so forth. So the way in which the load factor is distributed, we might want to put more load on the local device, on the centralized system, and this depends on the demand, on the supply, on the interest, on the distribution of power. Finally, momentum. AI is characterized by momentum. If you look at the investment in AI firms, there is, in 2010, there was $1.3 billion investment in new firm foundation, in new firm funding in AI, which raised to $40 billion, whereabouts in 2018. In 2020 has dropped, but because of COVID. So funding is growing steady year on year, 50%. But the point even here is that when you abandon the view of AI as a general purpose technology, but you see that AI is a large technical system, the momentum that pushes and drives the evolution of the technology might also be reversed. So, for example, the way in which AI could evolve is also affected by the within fights between the programmer community. It is affected by the availability of, or the expectation about the availability of free or open environment. And all these, it might also be affected by the end of the media hype about AI, when media discovered that it's not the case that all the jobs will be substituted by robots, because AI is not robotization, or not necessarily, or not completely overlapping. So the idea that AI winters might be around the corner has to be taken into account to understand the autonomy of evolution of the system. So to conclude, the contribution that we gave is addressing several communities of scholars. And in some points it might seem like, yeah, but you want to do a definitional exercise, but to label AI as a general purpose technology, when AI is not exactly a general purpose technology, might be detrimental. What we found is that AI is less pervasive than a general purpose technology, while having many spans, a large span of uses, is not widely used at scale. It is not unique, because the processes that adopt AI can be reverted back to non-AI approaches. So this is the prediction-based version of doing something like CV screening in HR. Doesn't mean that without AI, CV screening cannot be done. It has been done like that since forever. And the way in which AI influences innovation is more procedurally and qualitatively different from how a GPT influences innovation. So our contribution is that when we try the large technical system concept on AI, we uncover the fact that AI has to be treated as a system, because AI is becoming an infrastructural technology, similar to the internet, is large, but not as the pervasiveness of GPT suggests. It is now in the verge between innovation and growth and competition phase, and it's also experiencing technology transfer with different areas in the world developing this say infrastructural technology. It nicely maps onto all the features of the large technical system theory. And to conclude, we think that thinking in terms of AI LTS provides useful insight, or it is a better guide to see problems that otherwise, so theories usually should not necessarily solve problems, but should tell us where to look at. And seeing AI as a large technical system tell us where to look at. So which are the technological dynamics, the important mechanism at work, the way in which coordination unfold or not unfold, how standards can be set, and which are the influential stakeholder and system builder that can steer, might not have to steer, should not steer the direction of evolution of AI. So given that, thank you very much.
And we are ready to answer your questions.